Dear students, welcome to this lecture. So today I shall talk about cardinality. So here is the definition. So the cardinality of a finite set A is denoted by this symbol, or you can say the absolute value of A, and is defined by the number of elements of A. The number of elements of A. Okay, but if A is not finite, that is, if A is infinite, then we shall not say that the cardinality of A is the number of elements. But we use the term cardinality for an infinite set as well, and we shall use this term to distinguish several stages of infinity. Fine. So the cardinality this of an infinite set is used to distinguish several stages of infinity. So that's mean we will not ask that what is the cardinality of an infinite set. But if we have two infinite set, we will compare between them by their cardinality. So here is the first definition for the infinite set mainly, but you can use it is for the finite set as well. So here is my definition 1. So two sets A and B have the same cardinality that is that absolute value of A equal to absolute value of B if there exists a bijection F from A to B, or you can say there is a bijection G from B to A. That's mean if we have two sets, maybe finite or maybe infinite, but if there is a bijection between them, then we will say that they have same cardinality. That's mean cardinality of A is same as or is equal to the cardinality of B. Now here is my second definition. So this definition 1, 2, 3 is useful for infinite set, but you can use these definitions for the finite set as well. So now the second definition says if there is an injective function, say F from A to B, then we say the cardinality of A is less than or equal to the cardinality of the set B. That's mean we can use this one, less than equal to B. Fine. And we have another definition, say definition 3. So if there is an injective function f from A to B, but there is no bijective function between f A and B, or we can say H from A to B, then we say the cardinality of A is strictly, sometimes we may not use this term, but we will say that the cardinality of A is strictly less than the cardinality of B. That is, cardinality of A is strictly less than cardinality of B. We can see few examples. Here is the example 1. So, if we consider my set natural number and real number, then we have always an injective function f n to r defined by f of n equal to n is injective. Right? That imply, since we have a injective function from the set of natural number to the set of real number, therefore we can say that cardinality of n is less than equal to cardinality of r. Right? But we have also seen that there is no bijection between n and r, because n is countable and r is uncountable. Right? Since there is no bijection between them, therefore we have that cardinality of n is strictly less than cardinality of r. Fine. So we have another example, say example 2. So we can take two sets, say irrational number, say r minus q. Okay, we can rename this as a irrational number and r. Now again, if you define a map f from I to r by f of x equal to x, then f is injective, right? So that implies cardinality of the irrational is less than equal to cardinality of real numbers. Now the question is, are they equal? If you want to show that they are equal, then you have to find one bijective function f from the set of irrational number to the set of real number, right? Now here I shall construct one bijective function from the set of irrational number to the set of real number. So first of all, we know that the set of rational number q is countable, right? Now if we shift this q by root 2, then we will have a new set. So let A be a set which is just r plus root 2, where r belongs to q. Okay, then this is also a countable set because this set A has a bijection with q, right? Then A is also countable, right? Now since A is countable, so consider A as this set, say x1, x2, x3 in this way, right? So since the set A is countable, so we can list them as a sequence, right? Now again, A union q, that's mean this set r plus root 2 where r belongs to q, this set with q is also countable. Why? Because A is countable and q is countable. So being union of two countable set, this is also countable. So this is countable. So consider this set A union q as y1, y2, y3 in this way, right? So A is countable and A union q is also countable. Therefore, we have a bijection say G from A to A union q by G of xn equal to yn, where n belongs to natural numbers, right? Now what we will do, we will use this map to find a bijection from the set of irrational number to R. So first of all, note that the set I minus A is same as R minus A union q, right? Because what is my I? I is actually R minus q, and we again subtract the set A. So the left hand side will be I minus A and the right side will be R minus A union q. So they are same. Therefore we can define a map. So let H from this I minus A to R minus A union q, we can define this map just as identity, where h of x equal to x. right? Because they are same sets, right? Since they are same, so we can just define the identity. Now, by combining these two, we can define a bijective function from I to R, because my G is also bijection and this is also bijection. This we can write here, H is a bijection, right? So therefore we can define f from I to R such that f of x equal to g of x if x belongs to A and equal to h of x if x belongs to I minus A. So therefore f is a bijection from I to R. Now since there is a bijection from I to R, therefore the cardinality of the set of irrational number is same as the cardinality of R. That is, the cardinality of R minus Q is same as the cardinality of R. Fine. Now I shall prove one basic but very important lemma. So let A and B be two non-empty set. Non-empty sets. Then the following are equivalent. So first of all, this one says there exists a injective function f from A to B, and the second one is there exists a surjective function G from B to A. That's mean if you have a injective function from A to B, then you have a surjective function from B to A, and conversely if you have a surjective function from B to A, then you will have a injective function from A to B. Now here is the proof. First of all, 1 imply 2. So we assume that there is an injective function f from A to B. So let f A to B be an injective function. Okay. Now since f is injective, so if you restrict the codomain on fa, then you will get a bijective function. So then if we restrict the function to f of A, which is subset of B, so defining by, or you can say defined by this A, just my f of A. Okay, then this function is a bijective function. Right? So that's mean if we take the inverse, so if we take the inverse of this function from f of a to a is also bijective. Right? Now we shall extend this function, so we shall extend the domain. So how we shall extend the domain? So now choose a fixed point, so element a belongs to the set A. Now define a function g from b to a such that now g of b equal to f of bar that inverse b if b belongs to f of a, and equal to a if the point b is not in fa, or we can say b belongs to that capital B minus f of a. Right? Then obviously g is a surjective function. Then g b to a is a surjective function. So this proof is very elementary, right? And here is the next part. So 2 imply 1. Now we assume so g b to a surjective function. Okay. Now since g is surjective, so for each x belongs to a, g inverse x is non-empty. Right? This is the definition of surjective. Okay. And also this is a non-empty subset of B, right? Now clearly you can check that if we assume x1 not equal to x2, that imply if we take the set x1 intersection the set x2, that is empty, right? Now therefore g inverse x1 intersection g inverse x2, that will be empty. Why? Because this is just equal to g inverse x1 intersection x2. Now since this is empty, so this will be empty, right? So if we choose two distinct point x1 and x2, then g inverse x1 and g inverse x2 are disjoint, right? Now since they are disjoint, now we can define a function. Now define a function f from a to b such that f of x equal to y, where y is n arbitrary but fixed element of G inverse X. Now it is easy to check that if, say, first of all, so let f of x1 equal to y1 and f of x2 equal to y2. That's mean, so y1 belongs to G inverse x1, right, and y2 belongs to G inverse x2. Now it is easy to check that if x1 not equal to x2, then since this set, that is G inverse x1 and G inverse x2 are disjoint, so y1 not equal to y2. That imply f is injective. Right? Fine. So therefore, if we use this lemma, so we can say that if there is an injective function f from a to b, or a surjective function g b to a, then we can say the cardinality of a is less than equal to the cardinality of b. Now this leads to a natural question. Now if cardinality of a is less than equal to the cardinality of b, and the cardinality of b is less than equal to the cardinality of a, then can we say that the cardinality of a is same as cardinality of b? So the question is trivial in case a and b both are finite, right? And in that case, the answer will be true. Now this is true, or you can say trivially true, if a and b both are finite. Suppose the cardinality of a is m and the cardinality of b is n. Then if m is less than equal to n and n is less than equal to m, then m and n both are same, right? So this is a property of real number. Now if a and b both are infinite, right, then we cannot use that result. So the question is, if a and b both are infinite, then can we say that this result is true? Now actually this result is true for the case when a and b both are infinite. And this result follows from This result follows from a famous theorem of Schroeder and Bernstein. We can say follows from the famous theorem by Schroeder and Bernstein. Bernstein theorem. Now, what is the statement of this theorem? Now, here is the theorem. So, Schroeder Bernstein theorem. Now, this theorem says let f a to b and g b to a be two injective function. Now then there exists a bijective function between them. That means there exists a bijective function h from a to b. In other words, if you apply the previous lemma, then one can say that if a and b are two sets and there is a surjection or a surjective map from a to b and there is an injective map from a to b, that means from a to b you have an injective function as well as a surjective function, then there must have a bijection from a to b. That means there must have a bijection between a and b. Now here is the proof. So without loss of generality, we first assume that a and b both are disjoint. So without loss of generality, assume that a and b are disjoint. Given that f a to b and g b to a are injective maps. Right? Now choose an arbitrary element A from the set A and consider a sequence. This one. So first of all, since we have the point A, right? Now if we apply the map F, so it is belongs to A, right? Now if we apply the map F, then A will be my f of A and it will be in B, right? So this is belongs to A, this is belongs to B. Now again G is an injective map, right? So in fact it is a map. Since it is a map, so we apply G, we will have G into means composition with f of a. This is in A, right? Then again we apply f, right? So we will have f g f of A, right? And it will be in B. Now similarly we apply g and so on. So we have a infinite sequence in the right hand side. Now what about the left hand side? Now A belongs to A, right? Now we can apply the inverse of this g. Note that my small a belongs to capital A, but given that g is injective, right? So since g may not be surjective, so the inverse of A may exist or may not. So first of all we assume that if possible the inverse of A exists. Then we will have G inverse A, right? And we have a map G from G inverse A to A. Now again this is in B. Now the inverse of this term G inverse A may exist or may not, right? Now if the inverse of this term does not exist, then we will stop here, right? Otherwise, if the inverse of that G inverse A, it will be in B, right? If the inverse of G inverse A exists, then again we go to the next step. That's mean then we will have F inverse G inverse A. This is the map F and we will have A. This will be in A, right? Now again the similar logic. Now the if inverse of this element under the map G exists, then we will go further, otherwise we will stop here. Okay? So we will continue in this way, right? Now note that this sequence will not terminate on the right hand side. That's mean on the right hand side we have an infinite sequence, but on the left hand side the sequence will be infinite or not, or it will terminate. That will depend on the existence of F inverse and G inverse, right? So therefore we have few properties. Now the first property is the sequence will not terminate at right. Right? That's mean on the right hand side we will have an infinite sequence, but the terms can be repeated. Okay. Now the second property is the sequence may terminate on the left hand side, right? And when it will terminate, so this sequence will terminate at left if either F inverse or G inverse is not defined at some stage, right? As I mentioned earlier, so suppose the inverse of A under the map G does not exist, then we will stop here only, and if it exists then we will go here. Now again if the inverse under the map F exists, then we will go, otherwise we will stop here, right? So in this way we will know where to stop. So if there is no such stopping, that's mean we can have infinite sequence on the left hand side as well, right? Now we can say here if F inverse and G inverse exist, so both exist at each stage right, obviously at left, then the sequence will be infinite at left as well, right? But we know that the sequence is always infinite at the right hand side, right? Now if the sequence is also infinite from the left hand side as well, then we have two possibilities. Then the sequence is, so we say that if F inverse and G inverse exist at each stage at left, then the sequence is either doubly infinite so what is that doubly infinite? That's mean we know that at left and right all the term are distinct. That's mean at left and right we have distinct infinite elements. Okay, so in that case we will say that the sequence is doubly infinite. That's mean it will be infinite from the left hand side and from the right hand side as well, and all the terms are distinct, right? Now if the terms are repeated after some stage, then we will say the sequence is cyclic. So the sequence is either doubly infinite or cyclic. So what is the definition of cyclic? That's mean, so the terms repeats after some stage. In any case, we will not require to distinguish the cyclic and the doubly infinite. It is just a term. You can forget that one. Okay. So that's mean we have only two special case. So first one is the sequence will not terminate at right. That's mean it will be infinite at the right hand side, right? And the sequence may terminate or may not at left. We shall use these two facts to define the bijective map from A to B. So first of all, note that if any two elements of two sequence are same, that's mean if we have two sequences such that both sequences have a common element, then we can easily check that all of its right elements will be same, right? And this is just trivial because f and g both are map are functions, right? And also all the elements of its lefts are also same, and all of its left elements so if exist, it may not exist, right? So if exist, then will be same. Why? Because f and g both are injective. So since they are injective, so their inverse are unique, right? So if exist, if inverse of a point exists, then they are unique, right? So therefore, if we have two sequences such that they have one common point, then all the elements of its rights and all the elements of its lefts are same. That's mean the two sequences will be identified. That is, the two sequences will be same. Let's see this pictorially. So suppose we have two sequences, this and this, okay? Now suppose we have, say, this element and this element are same, so they are same. Now this map will be either f or g, right? So without loss of generality we can assume, so this is my f, this is my f, this is my g, g, f, f, and similarly, right? Fine. Now since this and this are same and this is just the image of the previous star, right, by the map f, so this will be again same. Now again, since this and this are same and g is a function, therefore this will be same, and similarly we can see that all the elements on the right hand side will be same, right? Now again, look at the left hand side of that identified element. Now again, look at this star. Now suppose the inverse of this star does not exist, okay, then we will stop here only, right? Now suppose the inverse of this star exists, then since g is a injective function, right, therefore this inverse of this star will be unique, right? So this will be same because both are the inverse of the function g of the same element, right? Now again, if there is no inverse of this element, then we will stop here, right? Otherwise we will again go further. That's mean we will take the inverse under the map f of this element. Now again, f is injective, therefore the inverse of this star will be unique, so this will be unique, so this will be same, right? And similarly we can see that all the elements from the left, right, all are same, therefore these two sequences are the same sequence only. That's mean we can see that whenever we have two sequences and if they have a common element, then both sequences should be same, right? So thus it gives one interesting fact. So first of all, we can say that, so thus if for any two element A1 and say A2, if this one, that is say A1, f of A1, gf A1, in this way it is going, and the other hand say G inverse A1, say f inverse G inverse A1, and again going, right? If this set intersect with the set A2, f of A2, G of f of A2, again going in the right hand side, and we are taking that left hand side element as well, say G inverse A2, say f inverse G inverse A2, and this way, right? Now if it, so this one says if the intersection of these two set is non-empty, then both set will be same, that is identified, right? On the other hand, note that, so if B belongs to a element of the set B, then what is my G of B? That will be in A, right? So we can make a sequence assuming A equal to G of B, right? Therefore, if we consider an element of B, of the set B, and we make a sequence, then we will get the same sequence as well, right? So therefore, since if we take the collection, that is if we take the elements of the sequence, then they are either totally disjoint, right, or they are same. Therefore we have a partition for the disjoint union of A union B. So therefore we have a partition for A union B, and that is the disjoint union of some alpha where belongs to some index set lambda, where the set is this. So A alpha, f of A alpha, G f A alpha, this as well as the left hand side element. Okay, and here we should mention that the left hand side that inverses can be empty after some stage. Okay, so that's mean we have a for each element in A, or you can say for each element in B, we have a sequences, right? Now if we take the elements of these sequences, then they are either same or they are totally disjoint, right? So therefore we have a partition of A union B. Now let A alpha equal to all of those elements of this partition, that is which is in A. That's mean the A alpha is my A alpha GAF A alpha, this one together with the inverses. So F inverse G inverse A alpha. So F inverse G inverse F inverse G inverse A alpha and dot dot all the elements. Fine. And say B alpha equal to, now F of A alpha, so F G F A alpha, this type of sets as well as the inverses. So G inverse A alpha, G inverse F inverse G inverse A alpha and all of these elements. Note that A is same as disjoint union of those A alpha, and B is same as the disjoint element of B alpha, right? Therefore this A alpha, this collection is a partition of A, and this collection is a partition of B, right? Now for each alpha we define a bijective function say H from A alpha to B alpha. Okay, and if we take the union of all of these bijective functions, then we will have a bijective function H from A to B, right? So now we have to do this one. Now note that this is not a difficult one. I can recall this one again. So what we did, first of all we choose one arbitrary element from A, and then we make a sequence, and this sequence has a property that the sequence will be infinite from the right hand side, and the sequence may terminate or may be infinite at the left side as well. Fine. Now we have seen that these sequences forms a partition on the set A union B. That's mean if we choose only the elements of A from this sequence, then it will be a partition of A, and if we choose only the elements of B from this sequence, then it will form a partition for the set B, right? And here we note that if we choose an element from the set B and we make that long sequence, then that sequence will be one of the sequence when we make a sequence assuming the element from A. That's mean it is fine if we consider the sequence by choosing the element from A only. Okay. Now what we will do, we will have a partition for the set A and we will have a partition for the set B, right? Now we will have, so we will define a bijection from A alpha to B alpha. Now if we have a bijection from A alpha to B alpha for each alpha, and if we take the union of all of those bijections, then we will have a bijection from A to B, right? So now my main concentration is that to find a bijection from A alpha to B alpha. Okay. Now first of all, if the sequence, so for each alpha, okay, so for each alpha, if the sequence stops obviously at left, because it will not stop at right. So if the sequence stops at a point of A, then we will have this kind of sequence, right? So from A we will have to B, so again A, again B, again A, again B, in this way, right? In this way, and there is no elements from A to this, so we will not have any element, right? So this will be stopped here. So if the sequence stops at a point of A, this one, then we define the bijection H from A alpha to B alpha, just as H alpha equal to, so it is not alpha, H A alpha, right? We just assume this is my f of A alpha. That's mean if the sequence stops at a point of A, then f of f restricted on A alpha, this will be a bijection from A alpha to B alpha, right? And we name that bijection as my H of A alpha. Fine. So this way we will define. Why? See, this is a bijection, this is a sequence, right? So this is my A. So we assume this one, we assume this one, we assume this one, and this way we can complete a bijection. So this is a definition. So how we are constructing a bijection. Now if the sequence stops obviously at left, now at a point of B, that's mean the sequence will be in this form. So B to A, then again B, A, in this way, right? So this is my G, this is my F, this is my G, this is my F, this is my G, this is my F, in this way. Now in this case we will define H in this way. So A to B, this is my H. So here A to B, this is my H. So this is my H. So in this way we will define H. Okay, that's mean then we define the bijection H A alpha. So A alpha to B alpha as H of A alpha will be my G inverse at A alpha, this one. Okay. Now you can easily check that. So here we have a bijection, here we have a bijection, here we have a bijection, and we continuing this way, then we will have a bijection from A to B for that sequence. That means we have a bijection from A alpha to B alpha. Now we have another case. So if the sequence does not terminate at left, then we can choose either F or either G. So anyone is fine. So the third case, if the sequence does not terminate at left, that is, the sequence is doubly infinite or cyclic, then f of then we can choose the bijection H of A alpha to B alpha as either f of A alpha to B alpha or G inverse A alpha to B alpha. Okay. So therefore, in each of these three cases, we get a bijection from A alpha to B alpha. Remember, when I defined that doubly infinite and cyclic, that time I told that, so there is no importance of that doubly infinite or cyclic in this case, right? This is just a term. So that's mean you have to just remember the sequence terminates at left or not. If it does not terminate, then we can choose either f distributed over A alpha or G inverse for my bijection, and if the sequence terminates at left, then depending on where it terminating, there we will choose either F or G inverse for my bijection, right? So therefore, we can say we get a bijection for each of the element of the partition. Right? So therefore, we have a bijection H from A to B, where H is just disjoint union of H A alpha. That's mean we can say that H is a map from A, which is just disjoint union of A alpha to B. which is just disjoint union of B alpha. Now we see one example to understand this theorem, and I hope that after the example you will understand this theorem. Now let's see one example to understand the previous theorem. So let A is my set close 0 open 1 and B closed interval 0 1, and suppose we want to find one bijection from A to B, right? So obviously finding bijection is little bit tricky, but you can always find one injective function from A to B and B to A, right? So consider the injective functions f from A to B such that f of x equal to x, it will work, right? It will be injective, and g from B to A such that g of x equal to x by 2, right? So it is also injective. Now by using f and g we want to construct one bijective function from A to B. So first of all 0 belongs to A, right? Now what is my f of 0? So f of 0 is 0, so 0 this is goes to, so if this is my A, right, then 0 goes to, by the map f, again since fx equal to x, so 0 goes to 0, right? Now if we apply again g, then again it will be 0, so it is just a 0 function, right? So in this case you can call it as a cyclic. Now suppose choose half belongs to A, right? So we have half. Now fx equal to x, so under the map f it will going to half, then it will be in B, so we will apply g, it will be 1 by 4, then again this is 1 by 4, right? So we can 1 by 8, 1 by 8, so this is in A, this is in B, in this way, right? So this is A, this is G, this is F, this is G, right? Now this is the right hand side, so it will going to the infinity. We know that right hand side it is always going to infinity, it will not stop, right? Now what about the left hand side of this half? Now is there any element in B whose image under the map G is half? Obviously g of 1 equal to half, right? So we have 1 which is in B such that g of 1 equal to half. Fine. Now what about the inverse of 1 under the map F? Is there any element? Now see, now fx equal to x, right? So the inverse of 1 should be 1, but 1 is not in A, therefore we do not have this 1. So this is my stop point, therefore the sequence stops at B, right? Now since the sequence stops at B, therefore how we will define the function A to B? So how we will define the bijection? That's mean we will define bijection A to B in this way. Right? That's mean by our theorem, so we define h of half equal to 1, h of 1 by 4 equal to 1 by 2, h of 1 by 8 equal to 1 by 4 in this way. Fine. And also if we consider the cyclic case, I forgot to mention that one here. Since it is cyclic, so we can choose either f or g as my bijection. Anyone is fine, right? So in this case, h of 0 will be 0. Okay, fine. Now suppose choose another element. For an example, suppose we have 2 by 3 belongs to A. Okay, then what is my 2 by 3? What is the image of 2 by 3? This belongs to A. So under the map F, it will be 2 by 3, right? Then under the map G, it will be 2 by 3 by 2. So it will be actually 1 by 3. Again by the map F, it will be 1 by 3. Then again by G, it will be continuing. This is in B, this is in A, this is in B, right? Now, is there element here in B whose image under the map G is 2 by 3? See, what is my function G? So Gx equal to x by 2, right? Therefore, if we have a function, if we have an element whose image is 2 by 3, then that element should be 4 by 3, right? But 4 by 3 is not in the set B, therefore we have to stop here, right? So we have to stop here, therefore the sequence stops at A. Since the sequence stops at A, therefore we have to define bijection in this way. That's mean F is my bijection in this way. That's mean we define, so we define h of 2 by 3 equal to 2 by 3, h of 1 by 3 equal to 1 by 3, and so on. Okay, now we can do this one for a general case. Now we know that h0 equal to 0 and h half equal to 1 by 4, right? H of 1 by 4 equal to 1 by 8, 1 by 4 equal to 1 by 2, h of 1 by 8 equal to 1 by 4, and so on. We know this one. Now we shall do the general case. So suppose half less than x less than 1, then that will imply 2x is bigger than 1, right? Now if we choose x is in A, right, then under the map F the image will be x, but the domain will be here B. Now again if we apply G, then it will be x by 2, right, and x by 2 will be in A. Then again if we apply F, then it will be again x by 2, but this will be in B, and then again we can apply G here, right, in this way. So we know that it will be continuing at the right hand side. Now what about the left hand side? Now what will be the inverse image of x under the map G? That's mean G, what will be this element? We know that Gx equal to x by 2. Therefore, G inverse x will be 2x. So that's mean we need here 2x, which will be the pre-image, that is inverse image of x under the map G, right? That's mean G inverse x would be 2x, or in other words G of 2x will be x. But see here, it is already given that 2x is already bigger than 1, so that's mean this will be bigger than 1. Now since this will be bigger than 1, so that will not be in B. So x does not have any pre-image, so therefore we have to stop here. So that's mean we can say the sequence stops at A. Now if the sequence stops at A, then our bijection H will be the same as F. Therefore we have to choose the bijection in this way, and we will get a bijection, right? So that implies H of x will be same as f of x. This is x, right? And when we have half less than x less than 1. Fine. Now similarly you can check that if 1 by 4 less than x less than 1 by 2, that implies 2x is less than 1, but 4x is bigger than 1. That implies if we have x and for the right hand side we have f, then g x by 2 x by 2, right? Then we have one preimage 2x, since 2x is less than 1, so we have 2x which is in B. Then again we will have again 2x which is in A, right? Now again if we need some function here g, if the inverse image of 2x under the map G should be 4x, right? But we know that 4x bigger than 1, therefore we have to stop here. Now again it stops at A. Therefore for such x, again we have to define my bijection in this way, right? Therefore h of x equal to f of x equal to x for all 1 by 4 less than x less than 1 by 2. And similarly you can check that for each 1 by 2 to the power n less than x less than 1 by 2 to the power n minus 1, h of x will be my x. Okay. Thus h 0 1 to that closed interval 0 1 is defined by, so we can say h of x equal to 2x for x equal to 1 by 2, 1 by 4, in this way 1 by 8, and equal to 0, sorry, equal to x otherwise. Now this is a bijection. Okay. So this completes the example. So I hope by using this example you can able to understand the proofs of the theorem. So we stop here. So in the next lecture I will start with the cardinality only.